Gravity versus acceleration. The original Einstein's elevator. Einstein imagined a sealed elevator with no windows, completely cut off from the outside world. The observer inside feels a downward force. But is it gravity pulling them down, or the floor accelerating upward through space? They can perform experiments inside using clocks, light beams, or any tools they bring with them. But without external references, Einstein argued, there's no way to tell the difference. This is the heart of the equivalence principle. In a closed system, gravity and acceleration are locally indistinguishable. Engineering time dilation with clock arrays. Let's look at a new version of the elevator, still sealed, still windowless, and still playing by Einstein's rules. But this time the interior is engineered with purpose. Here's the key insight. Clocks are part of the physical system, and time, at its core, is just the record of all the little changes happening inside that system. Energy gradients like gravity or acceleration don't just push objects around. They subtly change the structure and behavior of the system itself, including the internal mechanisms that define a clock cycle. That's why clocks behave differently in different parts of an energy field. We call this effect time dilation. And if we carefully design the structure of the elevator, routing those forces in distinct ways, we can use clock arrays to turn time dilation into a measurement tool. The elevator design. This is the internal structure of our engineered elevator. It's built around a rigid frame with both a top and bottom platform. Attached to that frame are 4 vertical clock columns. But here's the critical detail. Columns 1 and 4 are connected only to the ceiling, while columns 2 and 3 are connected only to the floor. Each column holds 3 clocks placed at 3, 6, and 9 meters above the floor. So at each height, some clocks are suspended from above, while others are anchored from below. This design creates a controlled asymmetry in how energy gradients travel through the structure, and that's what allows us to test for time dilation differences. Elevator accelerating in space. Now we test the elevator in space, accelerating upward at 9.8 meters per second squared, the same force we feel from gravity on Earth. From the inside, the observer can't tell whether this force is gravity or acceleration, but the clocks can, because in this case, the energy must flow through the structure. The floor pushes up, and the force travels through specific mechanical paths to reach each clock. Some clocks are connected through shorter, more direct paths, others through longer, indirect routes. As a result, the clocks don't tick at the same rate. Clocks C and M are farthest from the energy source, in a less dense part of the energy gradient, so they tick the fastest. Clocks F and J are closest to the source, in a denser part of the gradient, and tick the slowest. Time dilation appears as a clear pattern, mapped directly onto the structure of the elevator. This is the key. In an accelerating system, time dilation depends on how the energy is routed through the mechanical system. That pattern gives us a way to tell the difference. Elevator in Earth's gravity. Now we place the same specially engineered elevator on the surface of the Earth. The acceleration is still 9.8 meters per second squared. But here it comes from gravity, not motion. In this case, the energy doesn't travel through materials. Gravity creates a smooth energy gradient through space, and the clocks respond based on their height, not how they're connected to the structure. The time dilation pattern is different. The lowest clocks, C, F, J, and M, are deepest in the gravitational field. They tick the slowest, shown here in red. The middle clocks, B, E, G, I, and L, tick a little faster. They're in the middle of the gradient, shown in green. And the top clocks, A, D, H, and K, are farthest from the Earth's center. They tick the fastest, shown in blue. In Earth's gravitational field, time dilation depends only on height, because gravity flows through space itself in a uniform and distributed way, bypassing the structure of the elevator entirely. And that's how we know this elevator is sitting on Earth. Equivalent time dilation pattern. Now let's look at two elevators that would produce the exact same time dilation pattern across their clock arrays, but only if the specially engineered elevator on the right is inside a spaceship accelerating at 9.8 meters per second squared. That pattern would not appear if it were sitting in Earth's gravitational field. On the left, we built a second elevator, designed specifically to replicate the time dilation pattern seen in the engineered elevator during constant acceleration. This second elevator is structurally symmetric. All columns are rigid and uniform, and the clocks are placed at different heights. Because the structure is symmetric, this elevator would show the same pattern whether it's in a gravitational field or accelerating in space. We built it this way to help visualize what's happening inside the original engineered elevator when it's accelerating and routing energy through different mechanical paths. What we're really showing here is how clock arrays, combined with purposeful engineering, can produce measurable patterns of time dilation. And with enough clocks and the right geometry, we can turn those patterns into information streams that distinguish between similar systems to any level of detail we need. Darwin's Machines 2024. This solution to Einstein's elevator took me 40 years to work out, leveraging clock arrays, information systems, and discrete time to rethink relativity from the ground up. Everything here builds on Darwin's Machines 2024, your guide to structure-driven physics, clock arrays, and time dilations as environmental sensors. I hope you found this exploration of relativity, clock array experiments, and information theory valuable. If so, please like, subscribe, and comment.